Hello there.
Well, it currently appears that my camera is very choppy, so I don't know what happened there. But at any rate, good evening and welcome everybody. My name is Obi-Wan Pez. This is N-Simplex Pachinko. We are going to actually be working on some math communication today. I had accidentally hit start before I updated the stuff, the stream information, so we'll be redoing that. And then, very amusingly, I also did not update the other thing. Now, I also did not actually refit the ship. I was planning like, oh yeah, we'll do like, I don't know, 5 or 10 jumps to try and get to the next thing that we're trying to do, but then I forgot that we had taken off the fuel scoop and like literally everything from this entire ship. I think it's a 4. We want the fuel scoop 4A. Yep. And literally nothing else because we want to jump as far as we possibly can with this ship. Current 59 or 55.94 light years per jump, so pretty nice. Our current objective, we are starting in Huemo AA-A H256, which is pretty close to the galactic core. We're going to be heading over basically directly into the center. Where'd you go? That it? Nope. We are looking for a supermassive black hole, specifically the one located at Sagittarius A star. There we go. And we are trying to go just a little bit to the left over here in Stoeme. sector. Ooh, EGY. You know, it's pretty close to here. E, G, Y. Come on now. Doesn't want to give it to me. D, 1792. That's closer. It's real close. Okay, so actually, the science vessel is headed here. Which we also are not going to be able to get to faster than the ship itself. I think this one's only 27 jumps. Should only take a couple hours to do. Yeah. But... At any rate, we are going to be doing our regularly scheduled Math Communication Monday. Let's see. The one that we had is going to be on equivalence relations. Okay, here we go. Now we can actually scoop this star instead of sitting here and wondering why it's not working.
Warning. Frameshift drive operating beyond safety limits.
There it is.
Frameshift drive charging.
Hey, Fembox. Yes. So we're just taking a couple minutes to try and jump a few star systems over in Elite Dangerous, and then we'll be heading over to the arXiv article that we were looking at last week on equivalence relations. The point with that one was that there was a somewhat new definition, or at least a slightly different definition that the authors preferred. Rather than saying that equivalence relations are those structures, so relationships between two sets of either sets or numbers or what have you, equivalence relations are those which are symmetric. Ugh. What is going on with my computer? Those that are reflexive, symmetric, and the third one. You know what? I'm willing to bet that it is a combination between Firefox and Discord. Let's see real quick. Top. Nah, Firefox isn't doing too bad. It's only taken up about 13. Yep, thank you. Symmetric, reflexive, transitive. Yep. So yeah, those structures which have those three particular relations are themselves going to always be equivalence relations. So if they have all three, then the two things on either side have to be the same thing, or depending on what you're talking about, right? It's going to be equivalent. The issue that the author found was that the reflexive is actually somewhat redundant if you're saying that it's also reflexive is redundant if you are including symmetry, and there's one other little bit in there. So it's not like a minimally assured, minimally assured, damn it. Minimal assurance? Maybe. Something like that. So you're using the minimum amount of information in order to get... I'll clear out Firefox, see if that helps any. Oh. Firefox needed an update. That's maybe why it was throwing a fit. Nope, I'm still pretty choppy. So, yeah, so he said, you know, if we instead look at multiple other ideas that other people had already talked about in the past, then we're going to be able to say we could, in fact, use, in some cases, only two structures to assure equivalence. That's what I had meant when I was spouting all that. So, let me find the paper. Okay. That which means I need to restart Firefox, of course. And that one. And that one. Okay. Yep, so definition 1 by Asa. Helmut Asa. Is pretty much the standard for everybody, where it says it's reflexive, symmetric, and transitive. Let's get this archive link. God, hitting the wrong button. All over the place. And then Bertrand Russell changed things up a bit and said an equivalence relation Good evening, Zach. Welcome on in. We were just talking about the arXiv where we had left off last week, and I was also flying a little bit in Elite Dangerous to try and get us a little bit further. No, I don't want to be here. Hang on. Pro tip: do not start up your high heat electronics when you're next to a sun. Anyway, yeah, we're just flying a few, probably 10 jumps or so in Elite Dangerous while we just talk about stuff a little bit, which is exercising a pretty decent proportion of my mental capacity, so yay. It would probably also help if I opened this in my other computer so that I could actually see it. Why did you download? That is a terrible idea. We go for a ride on the neutron stars. Always fun. Anyway, so yeah, Bertrand Russell says that the equivalence relation on a set is symmetric and transitive, whose domain is the whole set. So here we say symmetric and transitive is all that's needed. We don't need this implication of reflexivity. It's redundant as long as you say that, you know, the domain is the whole set. Therefore, if it's symmetric, then it can be taken for granted that X has a relation to itself. Oh, goodness. Alright, and then Garrett Birkhoff said an equivalence relation is a relation that is reflexive and circular. So in this case, you could say as long as it relates to itself, and then it has a circular relation with, you know, any particular triplet, then, you know, it's perfectly capable. We're perfectly capable of coming up with that relation and saying that, oh, that is also an equivalence relation. And then looked like McLean came up with another definition, which again is similar but legally distinct. McLean came up with a slightly different formulation. It seems like everybody had their own ideas as far as, like, oh, what are equivalence relations? Hey, let me come up with another concept as well, just because, you know, if I were a very not quite stubborn is the right word. Not skeptical. What's the other? Cynical. There we go. If I were of a very cynical mind, I might say that, oh, pretty much everybody had their own definition because they wanted to sell their own book. Which, I mean, could be true. And we're going to park here and just recharge the fuel tank for a bit. Right, so McLean's autobiography helped to come up with a new definition from that. Why is this so far up? I can't. It's ridiculous. Okay, there we go. Nope. De Amicis came up with another idea here, which said that we could use a Euclidean relation where both 2 points x and z have a relation to y, and as long as the space that we're talking about is as long as the space we're talking about is reflexive and Euclidean, then a Euclidean relation says that if x and z both have a relation to y, then x and z have to have a relation to each other as well. Specifically, oh, right. But then also, as long as the space is reflexive, then it's also going to imply that not only does z have a relation to x, but x also has a relation to z. Because there was no difference between the two, right? Why do we happen to choose z first, then x, if the choice of statements said that both x and z have a relation to y? Like, there's no difference between them. So why do we choose z first? It's arbitrary. So we could have chosen x first. But if that's true, then x and z have to have a relation either way around. So therefore, that's not reflexive. Curses. No, that's just Euclidean. Okay, anyway. The letters are implicitly universally quantified, and therefore interchanging x and z is going to make that work. Okay. Symmetric, right. So, being reflexive and Euclidean automatically imposes symmetry on the other structure. And De Amicis came up with the term adequative to describe the Euclidean relation. Oi. The neutron stars do get kind of wild sometimes.
Operating beyond safety limits. Warning.
There we go.
Drive operating beyond safety limits. Frameshift drive supercharged.
Get us out of here. There was one neutron star that we actually got sucked into. That was not as much fun. We were trying to get to a planet which was like deep inside the gravity well, and when we got hit by the jet cone, it actually nosed the spacecraft into the star until we hit the exclusion zone. Once you hit the exclusion zone, you can no longer go to warp until you get out. But the issue there was that it was also...
Frameshift drive operating beyond safety limits.
it would also overheat if you... Or, no, sorry. It was still spiraling you down toward the star itself. Like, there was no escape then. And I tried, like, you know, facing upward to get out of it and all this stuff. And it just never... couldn't make it. So, we eventually overheated and blew up. And when I say eventually, it took a long time. It was very unfortunate. How long we got left? 15 jumps. Alright, so we're more than halfway. Nope. Sorry. Less than halfway. But only just. Right, so then the author of the paper says that, well, definition 5, this is on page 7, said, well, since we just talked about all that, we could just say that an equivalence relation is a Euclidean relation whose domain is the whole set. So now we're going off of Bertrand-Russell's definition and also off of De Amici's. So then, this says that Charles Buck in 1967 wrote in the New Math era that the equivalence relation is reflexive, symmetric, transitive, and circular. And this is, again, this is a theorem, which then you would have to prove as the student. So by just saying that it's a Euclidean relation and the domain is the whole set, you could then prove all of the other stuff. So it's reflexive, it's symmetric, it's transitive, and it's circular. All of them. Okay, so then we talked about De Morgan.
Warning. Frameshift drive operating beyond safety limits. Warning. Frameshift drive operating beyond safety limits.
Grr.
Frameshift drive operating beyond safety limits. Frameshift drive supercharged. Frameshift drive charged.
And And then also George Eliot, aka Marion Evans, who was alive in the 1820s to the until 1880. And she then formulated the axiom, things that have a constant relation to the same thing have a constant relation to each other. So this is, again, dealing with coming up with different formulations of what is an equivalence relation. Alright, so section the next is One Thing After Another, page 8, all the way at the bottom. An early triumph of the nascent concept of equivalence relation was the publication in the 1870s of two constructions of the set of real numbers, starting from the set of rational numbers. Dedekind's method was to partition the rational numbers into two ordered segments, partition of a set being a concrete way to realize an equivalence relation. Cantor's method, anticipated by Meret in 18 whatever, was to create the real numbers as equivalence classes of Cauchy sequences of rational numbers. So we talked about this a little bit in our real analysis course with Zach. Definition in Formula 1 of the introduction displays an intimidating thicket of quantifiers. It is not entirely wrong, but... even students who successfully parse the definition of limit as n goes to infinity of x sub n equals L, namely, for all epsilon greater than 0, there exists a capital N, such that for all m greater than or equal to capital N, the distance between x sub m and L is less than epsilon. Ooh, that's moving quick. Got it. Awesome. Yet the underlying idea is simple. A sequence can be viewed as an iterative process for approximating some particular number. A young child, unacquainted with trigonometry, has no difficulty finding a number that equals its own cosine. The tot need only open a calculator app on the parent's phone and tap the cosine button repeatedly until the display stops changing. The official definition of limit merely provides a guarantee that further taps will not change the result within the accuracy of the calculator. Oh, so close. I needed like another half second. It's just ridiculous. I used to do that with my parents' calculators back in the day. Not necessarily cosine, but you know, hit a button as many times as I can until something cool happens. Knowing the value of the limit L in advance is not critical. If the goal is phrased as certifying that a suitable stopping point has been reached in an approximation scheme, then Cauchy sequences can be described by a statement parallel to 5 Boo. Nope.
Frameshift drive operating beyond safety
Go.
limits. Frameshift drive supercharged. Frameshift drive charging.
Riker's Hope. It's a new region of the galaxy I haven't been to yet. Knowing that the value of the limit of L in advance is not critical if the goal is phrased as certifying that a suitable stopping point has been reached in approximation statement parallel to 5 using only 3 quantifiers. Sequence x sub n equals 1 to infinity of real numbers is a Cauchy sequence when...
Frameshift drive operating beyond safety limits.
Oh, that's tossing us all over the place, isn't it?
Frameshift
There you
drive supercharged.
go. Get us out. When for all epsilon greater than 0, there exists an capital M such that for all m greater than or equal to capital N, x sub m, the distance between x sub m and x sub capital N is less than epsilon. If this 3 quantifier statement holds, then the triangle inequality implies that the distance between x sub m and x sub n, lowercase, is less than or equal to the distance between x sub m and x sub big N, plus x sub little n, the distance between x sub little n and x sub big N is less than 2 epsilon. Alright, come on. There we go. As long as m and lowercase n are greater than or equal to big N. Consequently, the 4 quantifier statement holds with the innocuous replacement of epsilon by 2 epsilon. Stated informally in words instead of symbols, the definition with 4 quantifiers says that eventually the tail of the sequence has diameter as small as desired. Definition with 3 quantifiers says that eventually the tail of the sequence lies inside a specific ball of radius as small as desired. The second statement is more concrete, hence easier for novices to learn. Students at my university would bless an instructor who discloses that once they have mastered the definition of limit, they would also know the definition of Cauchy sequence. Simply replace capital L, limit, with the approximate value x sub n, big N. For half a century, I uncritically wrote the standard...
Hello there.
Hey, Poison Mouse, how's it going? For half a century, I uncritically wrote the standard 4 quantifiers, so discovering definition 6 was a shocking revelation. My amazed reaction echoed the exclamation of Thomas Hobbes on his chance encounter with the Pythagorean theorem. This is impossible! Relayed by John Aubrey. Embarrassed by the gap in my knowledge of rudimentary analysis, I compiled the following history to fathom how the needlessly elaborate statement 1 became canonical. Mathematicians in the late 18th century used infinite series to great effect.
Frameshift drive operating beyond safety limits.
Don't spit us out. Come on. Got it. Oi. There we go.
Frameshift drive charging.
For example, that the infinite sum as n goes from 1 to infinity of 1 over n squared is equal to pi squared on 6. This is a wonderful little identity. Yet the foundations on the subject were shaky. Indeed, when Jean-Laurent d'Alembert introduced a special case of the ratio test, he lamented that the proof given by Johann Bernoulli glossed over a, quote, mystery in the theory of series, a theory that appears to me still very imperfect. Hey. Didn't even see where the jet gun was. This is fine. 5 jumps. Oh, have we passed the ship? We passed the carrier. We'll be sitting there waiting for him. Awesome. Unsurprisingly, the first steps toward a rigorous characterization of convergence were taken in the context of the sequence of partial sums of an infinite series. The issue with the jump carriers is that they can only jump once every 15 minutes, and so that's how I was able to get so far ahead. It's every time we run through one of these neutron stars and jump with a jet cone, we can go upwards of 224 light years. The jump carriers can only do 500 light years once every 15 minutes. Gold is giving you gold in 2 hours? Oh no. Is it a contest? I do like contests. Right. Unsurprisingly, first steps toward a rigorous characterization of convergence were taken in the context of the sequence of partial sums of an infinite series. No formal theory of quantifiers was yet available, so the initial portrayals of convergence appear out of focus to modern eyes. Retouching the original work to fit the current conventions requires some guesswork about founders' viewpoints. Jose Anastasio da Cunha let's park under here, and then let's actually scan the place. Da Cunha, who died 2.5 years before Cauchy was born, defined an infinite series to be convergent when the sum can be terminated at some point. Oi. After which adding an arbitrary number of additional terms makes a negligible change. This statement can be plausibly interpreted as a version of Cauchy's criterion for convergence. Indeed, the 3-quantifier form seen above, more explicit, is the treatment in Cauchy's 1821 textbook, based on lectures at École Polytechnique, a necessary and sufficient condition for convergence of an infinite series. U0 plus U1 plus ... is that when n increases, the sums UN plus UN sub 1 versus UN plus UN sub 1 plus UN sub U sub n1 n plus 1 plus U sub n plus 2, etc., end up having absolute value less than any assigned positive bound. I interpret Cauchy's statement as meaning that the limit as n goes to infinity of the supremum as p is greater than or equal to 1 of the absolute value of u sub n plus all the way up through u sub n plus p is equal to 0. Right. So as we get to a particular value as n goes to infinity, so as we get arbitrarily close to the limit itself, we will technically reach that limit, quote unquote, when we have enough terms, i.e. n is close enough to infinity, that we're adding a negligible value for all particular p-values. So effectively, we're not seeing any change as we keep going further and further in the sequence. Wait a minute, that's silly. Check the system. Boo. Alright, fine. That's not what I wanted. That's what I wanted. Okay, so we got... A1, nothing interesting. A1A, nothing interesting. A3, nothing interesting. A5, nothing interesting. A5A, nothing interesting. Right, there are no human signals out here anyway, so that's not going to happen. A2, nothing. A4, nothing. Man. Alright, B7, nothing. B5, nothing. Atmosphere, 100% sulfur dioxide. That's fun. B6, nothing. B4, nothing. Goodness. This whole system's just stripped bare. B2, nothing. B2A, nothing. B3, nothing. B9, nothing. And B8, also nothing. Very sad. Astacon! Good evening and welcome. We're doing some Elite Dangerous tonight to jump out to... out in the Kreisue sector of the galaxy which is roughly speaking north of Sagittarius A star. We are on Distant Worlds 3. We're having some fun and poking around. We just made it past where the carrier is. So because we're in a Mandalay and we can jump 220 light years, 220 some odd light years per neutron. It's working out pretty nice. I didn't think we'd actually jump, you know, significantly beyond the carrier, but we did. Aye. We're getting pretty close to rendezvous system. And then we're also just reading some mathy stuff, so as I said, probably down there somewhere, we're technically doing Math Communication Monday, although it doesn't look like it at the moment. As soon as the once we jump into the rendezvous system and park, we will. That was the exclusion zone of a black hole. Jesus. It's fine. Right there. Right there. Yep, that's a black hole, everybody. One more time. Just to freak everybody out. But mostly me. Let's see. Yep. So let's go through and scan the system and see if we can't jump to one of these planets and land on it before the carrier gets here. So we can hand in some data and be the first people to land on it and stuff. So that's always fun. Ooh, wait. Nothing there. It happens. Nothing of note. 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 Still nothing. Nothing. There we go. For anybody who likes gaming type stuff, Asticon is an awesome streamer type person who has done a number of things. Is a variety streamer, likes Fallout, likes RimWorld, and has in the past been a GM for a version of the Elite Dangerous TTRPG. Woo! You also have an obscene amount of playtime. That is true, yes. No lie detected. I mean, there's a reason that they got you specifically to be the GM. Apart from being the one who drew the short straw and or said, yes, I will do that. And nothing there. Still nothing. My goodness. We're getting absolutely nothing in this system. It's too bad.
System scan complete.
Alright, well. How far away is this? 7,000 light seconds. Let's... Aw. That's too bad. 139,000, yeah, no thanks. Let's see. Oh, footfall, yep. Okay. How far is that? How far is that? The crap? You're not gonna tell me? That is terrible. Why would you do that? 5,600, that's not too bad. I mean, obviously you would have used the something of the grenade incident. That was hilarious. Of your own volition, yeah. Okay, nice. Still map it first. This is like, you know, essentially doing Gold Rush here. We're just trying to rush into places and like be the first to map something, be the first to put our feet on it, etc. Oops, too fast. Too fast. Ah. There we go. Alright, so we burn off some speed. And once we get back to 6, we pull back in. Let's see what happens. Yeah, a bit bigger of a planet than I thought it was. Alright, ads are going to start very shortly. Nice.
Surface scan complete.
There's nothing on here, right? Yeah, we are completely empty. Slip into the atmosphere.
Engaged.
As much as I want to hit those mountains over there, I want to land first. Gotta get down. Room. Alright, ads are going to start in 1 minute, and we'll take a 3-minute ad break, and then we will come back and, well, probably finish the probably finish the paper that we're looking at. And then we will most likely switch off Elite Dangerous and then turn on some music and look at yet another paper. We got a couple going still. Oops. Oh, you jerks. There we go. Quick, hop out. Okay, 3 minutes, everybody. Be right back. Thanks for coming. Got it. Hey YouTube, how we doing? Alright, that's that one. Discovered, not mapped. Awesome. Hate it when it does that. The inner ring. Alright, there we go.
Surface scan complete. Surface scanned by 50%.
Not really. Alright, where are we? Whole bunch out there. So, can we go like this? I have no idea how far that's going to go. Quite far. Okay. Do the same there. That should get us to 90. Righto. Welcome back. Nice. Ah. Too fat. Oh, yeah, I suppose. And then here we just need to toss one. Wait, literally just closer than that, and that should be fine. 1%. But still, 14 probes out of 21 possible, so did alright. Hey. Then go to the next one that is not landed on. Oh, okay. Yeah, that guy's going over there. So if we go here. Oh wait, no. Oh, damn. That was dumb. Not what I meant to do. Okay. Modern notation corresponding to the 4 quantifier condition. This is page 10. Bernard Bolzano had already formulated Cauchy's criterion 4 years earlier, stating as a theorem that a series converges when the indicated sums, quote, stay smaller than any given quantity if one has taken n large enough. Okay, fair enough. Stick that right in the corner. Burn off the extra speed. Come in a bit. It's a little close. It's alright. 7. Excellent. The details of Bolzano's attempted but failed proof suggest that he meant there exists a small n rather than there exists a big N for all small n greater than or equal to big N. Let's go. This is landable, right? This is landable, right? Oh, shoot. Nope. Not suitable for a landing. Cool. None of these are suitable for a landing except that one. We'll go there first. Famished, I am doing math. I am very carefully calculating trajectories in my head. And then when we overspeed someplace and we need to burn off extra speed, we keep the planet in the corner here and then just keep using yaw to turn our way in. But no, we're actually reading the archive paper that I listed above. Hang on. Copy, link, paste again. That one. So yeah. Oh, there's a biological.
Orbital flight engaged.
Nope. Okay. I don't know which particular blue area it's going to be. It's going to be the light blue one, or is it going to be the dark blue one? If it's the darker blue one, we need to go left. If it's the lighter blue one, we need to turn around. You're in El Salvador right now? Very hot? It must be about the same temperature as it is in my room. Fine. Oh wait, right. Footfalls. What? Come on. There we go. Get out, quick. Oh no, did somebody else get here first? So Crom. Or Marcus backward. Curse you! Well. I suppose I should have checked that first rather than going to the other ones, because... Right, first to map is just going to be the first person to get back on the carrier and sell all their info. Hey, Megamorph. I mean, some of them do have equivalence relations, i.e., are they really the same as each other? They are. They are procedurally generated, so it does make a rather interesting proposal. So we're talking about the archive link that I just posted. Again. And we are also waiting for the carrier that is jumping system to system to get here. In the meantime, you were worried that they would take it because it's broken? Oh no, you're worried they would take it, but since it's broken. No, that makes more sense. I really should have looked at what bearing we were facing when we originally got down here. Because now I don't remember what bearing we need to go. Cool. Alright, so we are looking for little teal spots in the snow. They almost all have exactly the same shape. and then they'll light if the reticle passes over it. It will turn blue. You know, it'll light up. It's already blue. There's one. So we need one more of these, approximately 1 kilometer away from either this one or the previous one. All right. Oop. Okay, thus the 3 quantifier criterion and 4 quantifier version were not clearly distinguished when the concept of convergence was first formalized, just as one does not differentiate nowadays between little epsilon and big epsilon, the 2 forms of that same letter. Of course, Bolzano and Cauchy and Cunha could not rigorously prove that a Cauchy sequence of real numbers converges, for a precise construction of the real numbers and a recognition of the need for a completeness axiom were decades in the future. The splendid abstract idea that a real number is an equivalence class of Cauchy sequences of rational numbers goes back to Meret, who used traditional sequences of rational numbers for a precise construction of the real numbers, and thus a recognition. Where are you? Ooh, don't do that. Still 2,500 away. Wait, what? What's this one? Bookmark. I mean, like, can I not? Oh, that's gonna suck. Ugh. Wait, what? The hell is the science carrier doing down there? What the that is no. That is no. No. There's nothing there. Don't understand. 0 light years. Oh, that's a lie. Okay, well, that is not possible. Carriers. Cool. Recognition for the need of completeness. Yeah, completeness axiom were decades in the future. Splendid abstract idea that a real number is an equivalence class of Cauchy sequences of rational numbers goes back to Meret, who used the traditional language of Cauchy without explicit quantifiers. Cantor's independent treatment of this construction explicitly supplied the epsilon and capital N in condition 1. Edouard. 。  . 。 . 。 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Cantor's elder colleague at University of Ada wrote a polished exposition of Cantor's method and stated the three quantifier condition. Thus, the twin characterizations not only hatched together but were sharing a nest when Cauchy sequences became recognized as a species of mathematical objects in their own right. The two coexisted for another half-century, but ultimately the ponderous definition knocked the lighter sibling out of the nest to expire from neglect. Cliches are strong with this one. I tend to notice that happens kind of a lot in arXiv articles, and I don't know if that's just a thing with arXiv or what. But yeah, the authors here really love their cliches. Come on. There we go. Okay, this is the last one. To account for the waning of the three quantifier definition, I propose the analogy of constructed auxiliary languages which were fashionable in the early 20th century, idealistic goal being to facilitate international understanding. Peano developed Latino sine flexione, Carnap, Maurice Fréchet, and Meret were all devotees of Esperanto. And Couture was an instigator of Ido, child of Esperanto. Yet in the 21st century, the constructed languages of interest to mathematicians are the ones to communicate with machines for the purposes of scientific computing, modeling, typesetting, generating conjectures, and validating proofs. Fashions change. The zenith of the sleek three quantifier definition was that of the first decade of the 20th century. Notable backers included English mathematicians such as E.T. Whittaker in the first edition of A Course of Modern Analysis, E.W. Hobson in his treatise on real functions, Jourdain, T.J. I.A. Bromwich in his book on infant series, French mathematicians such as Édouard Gaussat in his Cours d'analyse, and Fréchet in his thesis supervised by Jacques Adamar, and Belgian mathematician Charles-Jean de la Vallée-Poussin in his Cours d'analyse. As the decade ended, the darkness of war was upon the mathematician was on the horizon, and the Göttingen lectures on real functions by the Greek-German mathematician Konstantin Karateodori in the summer of 1914 were the last ray of sunshine for property before the long nightmare began. Global conflict affected mathematicians in many ways. Russell lost his lectureship for promulgating pacifist views unwelcome to the government, echo of what befell Bolzano in his country a century earlier. Jourdain, who was a disciple of Russell's mathematics but not his politics, fervently wished to contribute to the war effort. The Stephen Hawking of his time, a brilliant mind locked in a body ravaged by progressive neurological disease, Jourdain was rebuffed by a military unable to see past his disability. On the continent, Couture was possibly the first French fatality of World War I, killed on the very day that war was declared. He died in a car crash involving a military vehicle carrying urgent mobilization orders. Fréchet applied his language skills to serve as an interpreter for the British Army. Adama's two eldest sons died fighting against Germany in the endless Battle of Verdun. On the other side, Karateodori's Göttingen colleague Richard Courant was gravely wounded by British forces in the Battle of Loos. Courant had an outsized impact on the mathematical community in the post-war world. Everyone who has learned from a Springer Verlag book with a yellow cover has Courant to thank for persuading Ferdinand Springer to jump into mathematics publishing. Realizing a dream of Felix Klein, Courant built a mathematical institute in Göttingen. When the Nazi regime later nullified Courant's achievement by forcing out most of the faculty in 1933, Courant relocated to New York and created yet another renowned institute. His treatise about methods of mathematical physics, formerly known as Courant-Hilbert, is widely cited nearly a century after the initial publication. The relevance of this history is that the tipping point for this definition of Cauchy sequence seems to be the 1927 volume of Courant's first calculus textbook, which happened to use the four-quantifier definition. This influential volume went through multiple editions and reprintings in both German and English translation, although the three-quantifier definition was still extant, appearing in the 1927 second edition of the book on set theory by Felix Hausdorff, and in 1933 first volume on topology by Kazimierz Kurtowski. Its days were numbered. A quarter century later, a new generation of outstanding expositors adopted the four-quantifier definition in their books, such as Principles of Mathematical Analysis by Rudin, Mathematical Analysis by Apostol. Students of these gurus naturally copied the four-quantifier definition and passed them on to their own pupils. The books from which I learned and the books from which I later taught all use the four-quantifier definition, with the simpler three-quantifier definition of Cauchy sequence, rise again one day like a phoenix. Remark on terminology. Although I've been using the words Cauchy sequence throughout the discussion, this designation did not exist before the 20th century. No name was needed until the work of Cantor, whose own terminology was fundamental sequence. As far as I know, the appellation Cauchy sequence first appeared in Fréchet's thesis. I have restricted for simplicity to the motivating case of the Cauchy sequence of real numbers, yet the concept makes sense whenever there is whenever there is a notion of distance between the points. Natural setting for Cauchy sequences is a metric space, which is the next subject. So far away. The concepts of an equivalence relation and a Cauchy sequence developed on a time scale of decades as a trend toward abstraction took hold in the 19th century mathematics. On the other hand, the notion of metric space has a clear-cut 20th century definition in Fréchet's thesis, which has provided axioms equivalent to those stated in my introduction. Hausdorff standardized axioms in his foundational book on set theory and introduced the terminology metric space, nomenclature that became widely accepted despite Fréchet's reservations. These standard axioms are not minimal. One minor simplification, sufficiently well known to be recorded in Wikipedia, is to drop the assumption that the distance function is non-negative. as long as the distance is real valued, so that inequalities make sense, setting z equal to x in the triangle inequality and invoking the coincidence axiom shows that 0 is equal to the distance between x and x, which is less than or equal to the distance between x and y plus the distance between y and x. Therefore, by symmetry, the quantity distance between x and y cannot be negative. The redundancy of the hypothesis of non-negativity was pointed out in 1926 by Adolf Lindenbaum while still a student. He only made it to 37. Okay, nothing yet. Moreover, I find the coincidence axiom more intelligible when expressed in geometric language. The property says that the zero set of the distance function d is the diagonal, the set of ordered pairs having equal coordinates. The characteristic feature of metric spaces is the triangle inequality, already invoked in a previous section. The name harks back to Proposition 20 of Book 1 of Euclid's Elements. In any triangle, two sides taken together in any manner are greater than the remaining one. Apparently, Fréchet wrote the triangle inequality in one of the forms above to ensure transitivity of the informally stated relation. The distance between x and y is infinitesimal. Since circularity is a more powerful property than transitivity, the triangle inequality can be strengthened to a circular version. The distance between z and x is less than or equal to the distance between x and y plus the distance between y and z. Garrett Birkhoff gave the circular inequality a pleasing real-world interpretation, which I paraphrase as follows. If you take a plane trip from city X to city Z with a stop in city Y, then your return trip will be shorter if you take a direct flight home from Z to X. In theory. Combined with the coincidence axiom, the circular inequality implies that the distance function is symmetric. Indeed, setting Z equal to Y shows that distance between Y and X is less than or equal to the distance between X and Y. The variables are universally quantified, so the reverse inequality follows by switching x and y. Therefore, distance between x and y must equal the distance between y and x. In the presence of symmetry, the two triangle inequalities agree. Hence, the number of axioms for a metric space can be reduced from 3 to 2 by replacing the triangle inequality with the circular version and omitting the symmetry axiom. Dutch mathematician David van Dantzig anticipated Birkhoff by a decade in stating these two axioms for metric spaces, at the same time citing Lindenbaum's prior publication, which contains the circular inequality in a footnote. Lindenbaum wrote that he got the circular inequality from Piotr Zemensky, a fellow student at the University of Warsaw. Lindenbaum's own innovation was to replace inequality 4 not by 9, but in inequality corresponding to one of the figures we had above. Distance between x and z is less than or equal to the distance between y and x plus the distance between y and z. Interesting. So the distance between 2 points will be... Oh, it's... Yeah, okay, right. It's just symmetric of the other one. It's fine. X to Z is going to be the same or less than or equal to distance between X to Y and Y to Z was the way that it was stated before. This one is saying that specifically from that third point y, the sum of the distances going from there to the other two is going to be greater than or equal to the distance direct between the other 2 points. So that's really framing it from the perspective of point y, which is the third point it's the third point that is not on the line itself, or whatever it is in that particular metric space, because it doesn't have to be lines. I will call 10, the one we just described, the elliptical inequality, interpreting it as saying that the sum of the distances from a point y to an ellipse to the foci x and z exceeds the distance between said foci. Yeah, all right. Like the circular inequality, the elliptical inequality forces symmetry by setting z equal to y. Since the right-hand side is unchanged when x and z are switched, the left-hand side can be written either as d of xz or d of zx. Parallel argument shows that the right-hand side can equally well be distance between x and y plus distance between y and z. Z and y. This flexibility means that if you take the triangle in the way above figure and reassign the directions of the 3 arrows at random, you will obtain an elliptical inequality half the time, and the other cases will be split between circular inequality and standard triangle inequality. Hence Lindenbaum's definition of metric space. Why does it keep... I swear we keep getting pinged. Getting radar pings while we're out in the black is slightly disconcerting. It's fine. What do we have for stars here? Alright, let's flip our view screen over. So then this will also say, let's get rid of the desktop audio for the VOD. So, sorry everybody. For anybody who's here, that means we'll turn on our music. We'll also switch the window capture to jump over to the history of 3 wrong definitions, which is what we've been looking at. Hey, what do you know? Figure 3. Okay. Right. We also ought to give some credit where credit is due here. If anybody is so interested, go check out that music playlist there, and use your particular music / app / whatever, and make sure to give them likes, follows, and all that stuff. Share. Give them as much exposure as they can get, and play their stuff many, many times. Okay. Hence, Lindenbaum's definition of metric space seems the most natural. A metric space is a set E together with a real valued function D on E by E such that 1. The zero set of D is diagonal, and 2. The distance function of D satisfies the elliptical inequality. I mean, I hate it. Lindenbaum is remembered mainly for contributions to logic, in particular his collaboration with Alfred Tarski, but Polish mathematicians of the time were well aware of Lindenbaum's clever definition of metric space. Stefan Banach stated the Fresche-Hausdorff axioms in his seminal book on functional analysis, but mentioned Lindenbaum's improvement in a footnote. As did Lindenbaum's thesis supervisor, Wacław Szypinski, in his book on point set topology. Kuratowski, who had also taught Lindenbaum, jettisoned the traditional axioms in favor of Lindenbaum's. Understandable. If my students did something really awesome, I'd probably want to use it too. Solomon Lefschetz in America adopted Lindenbaum's definition of metric space in a book that standardized the word topology for the subject previously known as analysis situs. The indirect participation of Alice Berg-Hayes should be acknowledged. She and Lefschetz met as graduate students, and she had a teaching job before they were married. Although the social mores of the area precluded her from contemplating an academic career, she made a vital contribution to mathematics through helping her husband cope with the physical and psychological challenges of his disability. In his short-lived first career as an engineer, Lefschetz had lost both hands in an explosion of a high-voltage transformer that he was testing. Yikes. Although Lindenbaum's definition was noticed by some of the prominent researchers, most authors of introductory textbooks failed to follow suit, one exception being E.T. Copson in a Cambridge tract. I explained this circumstance through metaphor. Fresche and Hausdorff constructed an initial level of avant-garde skyscraper, the headquarters for two flourishing new corporations. First was point set topology in general abstract spaces, which had Fundamenta Mathematicae as its house journal. Sierpinski was also one of the founding editors in 1920, and Kuratowski joined the board in 1929. The other new entity was functional analysis, whose name was provided in a book by Paul Levy, taking a hint from his and Fresche's teacher Adamar. The supporting periodical was Studia Mathematica, of which Banach was a founding editor. 2 decades after the groundbreaking, when Lindenbaum proposed an elegant upgrade to the front entrance of the edifice. Yikes. Jeez. Okay. I don't know if you could also see that, but there's a black hole in here too. In addition to the two neutron stars. There we go. Oh, of course you can't see it. I took it off anyway. Anyway. 2 decades after groundbreaking, when Lindenbaum proposed an elegant upgrade to the front entrance of the edifice, crews were too busy building the upper stories to pay any much attention. Perhaps Lindenbaum's new design would have eventually been exhumed from the archives if not for the man-made disaster that shut down the construction site for half a dozen years. The catastrophe was the Second World War, antithetical to rational thought. Agreed. Amid universal suffering, some characters in this chronicle found abstract mathematics to be a solace in the dark, an affirmation of faith in the human spirit, or in extremis, an agency for preserving, if not one's life, then one's soul. When war broke out, Tarski fortuitously was overseas at Quine's invitation. Returning home to Warsaw was out of the question, but Tarski was aided by Carnap, Quine, and Russell to obtain an immigrant visa. The planned International Congress of Mathematicians, scheduled for September 1940 at Harvard, had to be cancelled. The German forces occupying Poland ransacked the universities, but Kuratowski got help from the Swiss consulate to preserve the draft second volume in his topology book by sending it to Geneva. As one throws things of value, if only to oneself, at the last moment out of a burning house. Rudin's family had got out of Austria after the Anschluss, going to Switzerland. And then to France. After the collapse of the French Third Republic, Rudin fled to England. In Vichy France, the peril for Jews forced Lévy literally to head for the hills and go into hiding. Adamar was able to secure a visiting position in America, but his last son died fighting with the Free French in North Africa. Tragically, many could find no refuge. Hausdorff and his wife, Tarski's parents, and Lindenbaum and his wife, who was the logician Janina Hosiasen, all perished in the Holocaust. Mathematical vocabulary evolves over time. Cauchy could call a list of numbers either a sequence or a series, but today's calculus teachers tell students that confusing these words is like mixing up American football with the football played by the rest of the world. Russell could speak of definition by means of principle of abstraction, but this terminology has been supplanted by the concepts of equivalence classes and quotient structures. These generalizations of metric spaces called class of V or class 5 ? In Fréché's thesis are obsolete, for they turn out to be metrizable. My leitmotif is that mathematical language can reach equilibrium by happenstance instead of by design. The steady state need not be a global extremum. This article has discussed the history of 3 definitions whose standard forms illuminate their subject with moonlight rather than sunlight. Takeaway message is that alternative definitions shine brighter and sharper. Equivalence relations can be characterized by one condition, the Euclidean property. Metric spaces can be defined by 2 axioms. The elliptical triangle inequality holds, and the zero set of the distance function is the diagonal. Cauchy sequences can be simplified through an inequality governed by 3 quantifiers. It's as simple as 1, 2, 3. No funding was received. They might be moored for the night. Let's see. Yep. Carrier's moored for the night, so they're going to be... Man, they're not jumping out until tomorrow night. Commander Gasper could come out here and spend like the entire night jumping through, or just, you know, hand over the controls to one of us. Not possible. It's too bad, really. Right, so I would hesitate in calling these like wrong definitions. I don't think that there's any actual issue with them, apart from the fact that they are not like minimal definitions. Which, as much as I like minimal definitions, right, something that doesn't require anything else, we could usually consider more elegant than something that requires a lot of what other fields might call priors. But I think it is interesting and usually important to show the history of where a concept comes from, even if it's not, you know, always going to be appreciated by the students. Weird that that dropped out. Anyway, input set. Some definitions can be considered morally wrong in some sense. I mean, like, if we're going to go through all this stuff, right? This statement here, right? Lindenbaum's definition of a metric space seems the most natural. If you are somebody who studies circular inequality and standard triangle inequality, and like this is your stuff, you know, this is what you talk about to your students all the time, then yeah, I guess you could say, okay, we've got this diagonal of our distance, essentially matrix, is going to always be 0, because those are talking about what is the distance from an object to itself. Right? And the distance function d satisfies the elliptical inequality. So, again, that's going to give us symmetry. just as much as any of the other stuff we've got. So 0 set of D, the diagonal, 0 set of D is the diagonal, is just telling us that reflexivity is the thing. Definition of a vector space is better described as an abelian group with an action ring homomorphism from F on to. I don't know what AUT is. It's probably a better way to understand vector spaces from an abstract perspective rather than a collection of axioms with little motivation. Endomorphism. Okay. Thank you. Because goodness knows I need a lot of help when it comes to abstract algebra. Yay! It's been so long. 22 years? Category theorists who may be biased. Yeah, well. I mean, I don't know. What axioms would you then be using to justify abelian groups and endomorphisms? I mean, I very well could agree with you. It's just... I'm just coming from, basically teaching high school and college level college students for the last, 15 years. Well, okay. 15 of the last 17 years. All right. All right, we already looked at this. Federico Adia was a guest on The Joy of X with Steven Strogatz a number of years back, and I only just got to listening to his exchange with Steven recently. Brilliant. If you've never listened to it, go look up the Joy of X podcast. Partly funded, I think, by Quanta Magazine. So it's a good listen if you're at all interested. And lately they've been doing like the Quanta podcast, but that's more like everything Quanta does rather than specifically mathematics. So what was this? Handbook of Enumerative Combinatorics. Okay. All right. Ads are going to start in about a minute, so just letting you all know. I'm going to get up, make sure that you get up, stretch, do all that good stuff. Do some like exercise or cycle your water or whatever else you need to do. And we shall return probably with a snack. I do have an atomic fireball here, but I've been eating the rest of these over the last, like, the rest of them, as in, like, no more in the entire world. My spouse came home with, like, a handful of them in a bag and was like, you know, I will take these to work, but if you want them, I was like, I'll take one. And I took one and expected that she would just take the whole rest of the bag to work. Yeah, never did. So I have been eating them like one a day, and the insides of my cheeks, I swear, are just like abraded from cinnamon. All right, heading out for snack and water and all that good stuff. So see you all in 3 minutes. Thank you so much for coming, and be right back. And of course, we will do a little bit of Tai Chi. So, we'll get through the amount of the form that I have done. We got some new step or two on Saturday. We'll see how much of it I actually remember. So, basically instead of just doing a standard trunk rotation, this is a warm-up, so I recommend anybody who wants to get up and be a little bit more active, go ahead and do this. So here we kind of spin at the hip, and instead of just doing a normal trunk rotation where we like let our arms go just kind of wide, what we're doing is we're pulling them close to the body and then just kind of letting them swing from there. So try not to like force them into or out of any particular movement. It's just that it increases the speed at which they move when they hit the downswing. It increases the G-forces and pushes some of the extra blood down into your hands. It also then, these exercises, generally speaking, are good for flexibility and increasing the flow of synovial fluid in your joints. So it's pretty good stuff. These are exercises that have been passed on from teachers to masters to the teachers to the students in Malaysia, where my particular instructor's Tai Chi lineage comes from. So, I think this is Master Huang. I think that's right. It's been a while. So in addition to this, we also go this way. So we just bounce the knees a little bit, and just like a kid on a swing, you just kind of put a little bit of energy into your hands every time they come down, and then straighten up a little bit as they fling backwards. And again, builds up some energy, builds up some speed, and that also builds up power if you actually end up using this in actual Tai Chi and actual, like, fights. It's not like you'd be doing this. It looks silly, but rather you would use essentially the power that you store into your hips and the inguinal creases. And so effectively what this becomes is the ability to stay relaxed, stay focused, and be able to throw techniques from the hip. So doing things like that, anyway, ends up being pretty helpful in the long run. It's also really helpful if you're over 40. Do some Tai Chi. One of the other ones we do, we lean back, keeping the our weight forward on our toes as much as possible, or on the balls of our feet as much as possible. Lean back as far as you can, and then straighten up. Come down to the middle. You just kind of squat a bit, and then try not to go too far, but just basically like lean straight back into this again. And this is done like, 10 times or something like that. But again, this is just to get limber, start doing some exercises, start getting moving, and increase the amount of synovial fluid that's in your joints. From here, usually you bend all the way down and kind of sweep the floor back and forth, and then rotate arms at the shoulders. I'm not going to do it quite here just because you can't really see what I'm doing, and it looks a little bit weird. And then go do a trunk rotation as you're squatted down, bent over, so that your arms are kind of slapping against the sides of your legs. Again, just loosen up. Then we put 1 foot forward, 1 foot back. Do the same sort of thing here. Keep a little bit of tension just in the fingers, like you're reaching forward a little bit. Usually this is done with what's known as tiger's maw. So you keep your hand essentially like this and just keep doing this. Again, number of times. Transfer the energy, the weight from balls of your foot to balls of your foot, and then switch. There's some really good cool down and stretching exercises, which involve breathing, obviously, but they involve specialty breathing. So when we're done, we've been doing this kind of like you breathe in and then out and then in and then out. And when you go down, you try and touch the floor with both your hands as flat as you can. And you stay there for 3 seconds essentially, and then come back up, breathe in and then out, and then in and then out, reach down again. And as your mind becomes more relaxed, and as your body gets more relaxed into the breathing and into the stretching, then you end up actually being able to touch the floor with more of your hand. So like I have pretty long legs compared to my torso. And so like the reaching down and trying to touch the floor, I essentially end up about here every single time on the first one, where I'm just touching the tips of my fingers and I'm not getting the tops of my palm here, the base of the fingers. I'm not touching the ground almost at all. And then on the second one, I'm almost always like complete flat hand on the ground. And the third one, I'm actually like pushing back, taking some of the weight off of my feet and putting them onto my hands instead. So it definitely works. It's definitely a really awesome thing. All right, so as for the form, we stand in bear stance like this, and our feet are in a V shape right in front of us. We then tuck into the right inguinal crease, shift the left foot to straight ahead, move it across, and then come across like this, straighten the right foot. Then we breathe in for 2, out for 2, tuck into the left inguinal crease, come up with an quote-unquote energy ball, and turn on the right heel to come this way. We come through. That is wrong. Hang on. No, that's right. Okay. Shift almost all the way to this side and twist in. And then when we do that, we tuck into the inguinal crease again, step forward with the left, come up with a ward off, and right hand stays low. Twist until our body is more or less straight. Back leg is approximately 45 degrees off to the side, whereas front leg is straight ahead. And then from here, we turn on the tuck into the inguinal crease, turn on the ball of the right foot, step forward as we switch into a ward off right, turn on the left heel until we're back in straight ahead, forward, and 45 degrees on the back leg. And then we roll back, shift weight to rear, press, and then push. As we come back to the front, and then we twist even further, come down with a single whip in our hand here, and then the lower hand is just underneath it. And as we twist even further, the tension gets released as we snap a single whip to the right, step left in a defensive posture, and then we make it more aggressive by shifting our weight to the front, turning the hand so that our left wrist is now bladed against whatever we might be touching, and the rear foot twists in again as well here. And then we go into lift hands, come back and shoulder strike, and then we tuck into the right inguinal crease and shift turn on the left heel to come to forward, and then the hands come across into white crane. Here we do a brush knee, and then we do strum the lute. So we step up with the right foot, essentially 90 degrees to the left foot. The left foot is now well in front, but on the heel, basically putting no weight on it. And then our hands are down up like this. They were, what was I doing? I was going this way, right? They were here. So we step in, switch their locations essentially. And then from here, we do another brush knee. Then from here, we lean back, come up on the left heel, and then come down at 45 degrees and make our fist with the right. And then we twist into the left inguinal crease, come through with a back fist followed by a parry. And then we step through and punch here. Usually that also involves a twist of the back leg so that it's now at 45 degrees. Then we do what's called a rufong subi, where we tuck into the inguinal crease. We shift our top hand underneath. We then take the weight off of the right hand with the left. And then we come back and we push. Shift the weight back again. Twist to the front. This comes out, up, and we hold. The weight of our left hand is basically given to the right wrist. We want our elbows to be up and away from the body, and like 70% of our weight is now on the left foot, which for most, if I was in karate, this is really weird because most of the time when we're standing in like horse stance, our weight is 50-50. Both of our feet are pointing in the same direction. They're equal, even with each other, so it should be 50-50. In Tai Chi, it's never 50-50 because you will get knocked over. It only takes essentially half of the force to cause you to fall over. All right, for that we drop the right hand, come up with the left around our ear, and then as we do this, we turn out on the right heel. No, turn out on the right ball of the toe. Yeah, there we go. Ball of the foot as we move there, and then we step back at 135 degrees. And then we do what's called carry tiger to mountain. So generally speaking, tiger is someone who is very aggressive. And so from here, we're like underhanded grabbing a belt or very much not a belt. And here we take either their hand or their face or something like that. And then we basically just shift our weight to the right, over to the right foot. And as we do that, we come through, twist, and move, turn on the right, no, That's the left. Turn on the left heel so that everything just kind of comes together. So from here, kind of twist all that together and then throw. From here, we bring the right hand up into a rollback, press, and push. This becomes a very familiar pattern. And whip to the front. From here, come down, and again, single whip here, with this hand coming out as well. We're now at 45 degrees. We come back, right, so we should be, shoot. We came this way, we come that way, we whip here with this out there, we're on the back leg, and then we lean in with the front to become bladed on the left. Then we lean back, come back to the front here, so that we're effectively going to 90 degrees, and then we whip through. So this is going to be effectively a slap as we step with the right, and then as we step with the left, we're going to put elbow under and pop something. Usually, again, this whole structure is coming forward, and we're using the momentum of the body to do the actual work on this move. So you'd like engage this at some point and then step into it, and the entire 90-ish kilos of my mass will then be pushed into somebody. Right. So then this comes back, come back to the ear, step back, toe, heel, and this then is a retreating step. It's called repulse monkey. This comes back up here. We do the same on this side. Repulse monkey, and then we do a third because we totally have room for this. This comes up to the ear, steps back, repulse monkey again. These then switch position, and we do another step for 135 degrees over here. Right foot's going to be in front a bit, and then when we come through and twist, this is going to be sort of a push at the chest. Oh, I'm out of the camera here. We're effectively coming up, probably contacting somebody about here, and then push. So again, we're using the weight of the body to do most of the work. And if you also use your right leg to hook under their ankle, you can push them over real easy because they're just going to trip over your leg. Honestly, I can't wait to bring some of this stuff back to karate because they'll be like, the hell did you learn that? Right, so push like that. Then we come through, tuck, and energy ball again. Step with the left further. Come up with cloud hands. Step feet together. Cloud hands to the right. Step. Cloud hands to the right. Step. Cloud hands to the left. Step. Cloud hands to the right. Step. Cloud hands to the left. Step. Cloud hands forward. I never know where to stand. Then when we get to here, we're going to tuck right, and then this becomes a single whip to the front. It's effectively like a gooseneck sort of thing. And then from here, we're going to twist this up and this out at the same time. So from here, it kind of goes like that. And then instead of doing the bladed thing with the left hand, we're going to come down, twist in, grab the calf of the person that's in front of you right around the ankle, and then we flip them up like this, and then this comes here. Whoops, here. We make a nice little block for any kicks that might come up this way. Right, and then this comes down, and this comes up, and then when we do this, we have to twist in a bit. We step back. This comes through as a retreating strike, and then this one comes through, and this is about the last few steps that I learned, and now I can't remember. But we'll get retaught all of this again on Wednesday. And it's been damn near 20 minutes. So, so we're getting in our exercise for the day. All right. Exercise tomorrow will also include mowing the lawn. Oh, goodness. Ew. Why is that off the screen? Ew. Why would you do that? All right. Good enough. And of course, I would be remiss if I did not mention that we are working this month with GoTell. That is all the way at the bottom, not the one right here, the one all the way at the bottom, which is working through Tiltify to run the Game On to End Lupus 2026 fundraiser. So if anybody is interested in if anyone is interested in donating to the Lupus Foundation of America, we are working with Coco Confession, 8BitD, L-Bell, and a number of other friends in order to fundraise for Lupus Foundation of America. Lupus is an autoimmune disease that does terrible, awful things, and we don't really know all that much about it, unfortunately. Because it expresses itself in effectively like the same number of different ways as there are people who have it. So unfortunately, it gets misdiagnosed a lot, and a lot of people who have lupus, their doctors are like, I mean, I don't know what this is, and then eventually they get tested and find out, oh, what do you know? It's lupus, and person's like, great, now what does that mean? And the doctor's like, oh. Not to say that the doctors like don't know entirely. It's just that it's this weird autoimmune thing that does terrible things until people eventually succumb to one of its many different effects. And so it is quite awful. It can be degenerative. It can just keep at kind of a steady pace throughout the rest of the person's life. It's like the old joke, you know, if you ask 100 teachers what their opinions are on, or if you ask 100 teachers what their preferred teaching method is, you will get 100 different answers, or you will get 105 different answers, or something like that. It's kind of the same thing with lupus. If you have 100 lupus patients in the room, you will have 105 different ways of lupus expressing itself. So it's very strange and unfortunate, and we would like to raise money in order to help people, and also to raise money for research. So currently, a lot of lupus research is being cut because science funding in the United States is being cut quite a lot. So if anyone is so inspired and has the ability to do so, you can get the QR code down at the bottom for Tiltify, which then brings you to the that way Game On to End Lupus campaign for 2026, which is benefiting the Lupus Foundation of America. If you would also like to do it on one of the other people's pages, that is perfectly fine too. We have some community goals, which are, if you go to the GoTell page, my campaign link will have all of the individual donation benefits / punishments to me. If you would like to see me eat something extremely hot, right? We have the pepino peppers right here, which are rated an 8.5 on the hotness scale for Don Enrique. We also have the slightly lower de arbol peppers, which are, I believe, a 7. These are dried, hence why we have them in rice as well. A little bit of rice in there with it. If I get some of the, not just the pepper itself, but some of the seeds in there, yeah, it's she spicy. And then we also have a number of donations where you get to purchase a math subject of my choice, or of your choice, not my choice, of your choice. And I would prefer something within my grasp. A lot of these papers that we read here are well outside of my understanding. I do try as much as I can, but eventually they start slipping past my ability. And so some of these I will not be able to teach that particular subject. But if you want to work with me, we can make it work. My ability, generally speaking, is like undergraduate mathematics. If we wanted to start talking about PDEs or combinatorics at a graduate level, like I've done some of this stuff before, so maybe we can figure it out. But at any rate, tonight is hashtag not sponsored by Vocation Brewery's Love and Hate New England IPA. There we go. Ugh. Yeah, we went to Beauty and the Beast at quote-unquote Baltimore. It's not Baltimore, but it's close enough. Toby's, which is a dinner theater. Very nice. If you ordered a fancy drink, then they would give you a pint glass to take home. So we would often go to Toby's, get the fancy drink, whether that was just a milkshake or something with a bit more oomph to it. Very hoppy, a little bit of pininess to it. Okay. So we were looking at the algebraic and geometric methods in enumerative combinatorics to try and understand some of the ideas that were in enumerative combinatorics so that we could try and understand what was going on here. This was by Federico Ardea. Right, so this is pages 1 through 20. We're just like in the first, not quite this. Yeah, okay. So we had gone through to generating functions. What is a good answer to an enumerative problem? Not surprisingly, there is no definitive answer to this question. When we count a family of combinatorial objects, we looked for explicit formulas, recursive formulas, asymptotic formulas, and generating functions. They're all useful. Generating functions are the most powerful framework we have to relate these different kinds of answers and ideally find them all. In combinatorics, the most useful ways of determining a sequence of numbers a0, a1, a2 is to compute its ordinary generating function. A of x is equal to the infinite sum n greater than or equal to 0 of a sub n times a x to the n. So effectively, this is an infinite polynomial. It could be finite because after a certain point, it is allowed to have all zeros for its coefficients. That's perfectly fine. This is done in Taylor polynomials. This is done in other generating polynomials. So it kind of depends on just what you want. The exponential generating function is the exact same thing as this power function, but then it's got an n factorial in the denominator, which then cuts it off, makes it reach the particular function you're looking for asymptotically a lot quicker. The issue with ordinary generating functions is that as x gets larger, we start having larger powers, and so our coefficients have to similarly decrease very quickly in order to start approximating our whatever function it is fairly quickly, or else they start growing too large, and then like you have essentially an you have a radius of convergence in which your x values are helpful and meaningful, and outside of which they're extremely not. The exponential generating function typically ends up working a lot better because our n factorial will converge much more quickly than a power function. So we will end up with a function that approximates whatever function it is that we're looking for a lot faster and a lot better. This simple idea is extremely powerful because some of the most common algebraic operations on ordinary and exponential generating functions correspond to some of the most common operations on combinatorial objects. This allows us to count many interesting families of objects. This is the content of section 132 for ordinary generating functions, 133 for exponential generating functions, and in section 134, which is not included in this document. We see how nice generating functions can be turned into explicit, recursive, and asymptotic formulas for the corresponding sequences. Before we get into the interesting theory, we have to understand what we mean by power series. Section 131 provides detailed discussion. Probably best skip for the first time one encounters power series. Honestly, if you're approximately like calculus 1/2, you're going to get it. If you're pre-calculus level, it might be a little bit challenging, but honestly, you've seen series before, probably. So if you've seen series before, you can, in theory, understand some of the ideas that are going on with power series. There are also going to be ideas such as limits, which might be kind of on the edge of your abilities, but that's fine. Don't worry about it too much. We've only got 12 pages to go. So there are two main attitudes toward the power series in combinatorics: analytic and algebraic. To harness the full power of the power series, one should really understand both. Not surprising. Chapter 2 of this handbook, which again, not included in this document, is devoted to the analytic approach, which treats a of x as an honest analytic function of x and uses analytic properties of a of x to derive combinatorial properties of a sub n. In this chapter, we follow the algebraic approach, which treats a of x as a formal algebraic expression and manipulates it using the usual laws of algebra without having to worry about convergence issues. Again, like I said, we can have what's called a radius of convergence if our a's are going to be just any old particular a's. It's only going to be a useful power series over a certain set of values of x. So it will center around a particular point, and then as we get further and further away from that point, the approximation becomes less and less useful, less and less good of an approximation, and then at the edge of the radius of convergence, it will switch from being a useful approximation to being extremely not. Once we go outside of the radius of convergence, it no longer converges, surprisingly. And then what happens is we see that this thing will diverge, and it goes off to infinity, because now our x's are overpowered. They will be raised to certain powers. And then eventually n starts going off toward infinity. So x to the infinity now is going to be greater than 1, which, well, okay. The x term ends up having a value that is greater than 1 and is unchecked in any other way. And so a number that's greater than 1 going to infinity, or with a power that goes to infinity, is going to itself go to infinity. So it needs to be checked in some way, shape, or form in order to make sure that that infinity is going to be like divided by a more powerful infinity, so it goes to 0. And those individual terms start going to lower and lower and lower values. We'll see it. All right, the ring of formal power series. Enumerative combinatorics is full of intricate algebraic computations with power series where justifying convergence is cumbersome and usually unnecessary. In fact, many power series in combinatorics, such as this one, n factorial times x to the n, will only converge at 0. X equals 0. So analytic methods are not available to study them because, again, as our n gets big, n factorial is big, and x to the n x to the n is also going to probably be big. But even if x is a small number, like 0.0001, raising that to the nth power as n gets very big is going to make 0.00001 to the n a very, very small number. However, n factorial is humongous. If anybody doesn't know what factorial is, you take n, and then you take n minus 1, and n minus 2, and n minus 3, and n minus 4, and you multiply all of them. So you take the product of n and every integer before it all the way down to 1. So let's look at that, right? 1 factorial is just 1. 2 factorial is 2 times 1, which is just 2. 3 factorial is 3 times 2 times 1, which is then going to be 6. 4 factorial is 4 times 3 times 2 times 1, which is 6 times 4, which is now 24. And then 5 factorial is 5 times 24, which is 120. So this grows insanely fast. It's something that you won't be able to fully appreciate until you see like the rapidity at which various functions increase in their value. So power functions like, x to the n, right, are not particularly fast. X squared, x cubed, x to the fourth. Right? These are polynomial functions. They increase quickly, but honestly, they're not that fast. X to the x, a tower function, grows incredibly fast. However, x factorial will grow much faster eventually. So it starts out kind of slow, right? 1 times 2 times 3 times 4 times 5. But very quickly you're multiplying by 10 and by 20 and by 30. And those previous powers just compound very quickly. For these reasons, we often prefer to carry out computations algebraically in terms of formal power series. We'll often see that in this approach, analytic considerations are often useful. In this section, we review the definition of basic properties of ring of formal power series. C brackets X. I'm not really sure. I think, right, because we're allowing for complex numbers as our coefficients, a sub 0, a sub 1, a sub 2, etc. For a more in-depth discussion, including the mostly straightforward proofs of the statements we make here, see reference 149. Now, I don't know if this is page 8. No, we don't have it here. Cool. Page 8. Formal power series is an expression of the form a of x is equal to a sub 0 plus a sub 1x plus a sub 2x squared plus, etc., where all of our coefficients are complex numbers. Formally, this series is just a sequence of complex numbers, etc. We will see that it is convenient to denote it a of x, but do not consider it to be a function of x, interestingly enough. Right? We only really plug in the x value like way later, if we actually want to think about it as needing a particular x value plugged in. Most of the time, we're looking at this and saying, like, what function of x is this thing? So, in terms of Taylor series, we look at this and say, like, how do we represent e to the x? Well, this is going to be, goodness. I think this is our 1 plus e to the x Taylor. Taylor series expansion of e to the x. Oh, of course you're not going to give me that easy. There we go. Yeah, 1 plus x squared on 2 factorial plus 3 squared. Nope. Plus x cubed on 3 factorial plus x to the 4th on 4 factorial, etc. So there's a bunch of really cool stuff that you can throw in and note that that we can in fact get a function of x represented as a Taylor polynomial, which is again, polynomial with these factorial terms in the denominators. What they're getting at here, what Federico is getting at here, is that we don't really think of it as like a of x is a function of x. Really, we're thinking of it as a of x is approximating another, and you guys can correct me if I'm absolutely wrong on this, but the way I understand it is that a of x really is the approximation in terms of an infinite series of some other function of x. And really what we care about is like, which function is this? Let's see bracket x be the ring of formal power series where the sum and product of a of x and b of x, given here, two power series, are the following. So a of x plus b of x equals the infinite sum of a sub n plus b sub n times x to the n. Whereas the product a of x times b of x is equal to the infinite sum of n's, going from 0 off to infinity, of the coefficients infinite sum as k goes from 0 to n of a sub k times b sub n minus k times x to the n. That one's fun. So we picked a particular k. And we have a particular n from this one over here. And we say that we're going to go from, again, k equals 0, all the way up through k equals n, where n starts at 0. And we're going to cycle through all of the possible b coefficients. And we're going to make a sum of all of the combinations of a sub k, which in this case, like first one's going to be a sub 0 times b sub, n will be 0, k will be 0. So that's going to be a sub 0, b sub 0 times x to the 0. So there's only one number there. Then we go through and say, okay, when n, that's it for the middle one. Then when n cycles up to 1, then we come in here and say k equals 0 to 1. So there's going to be two terms here. Where k is 0, we get a sub 0, b sub 1 minus 0. So a sub 0, b sub 1 times x to the 1 plus a sub 0, b sub a sub 1, b sub 1 minus 1. So that's 0. A sub 1, b sub 0 times x to the 1. Right? And then we keep moving up and up and up. It's implicit in the definition, but worth mentioning that the infinite sum of a sub n x to the n is equal to the infinite sum of b sub n x to the n if and only if a sub n equals b sub n for all individual coefficients. For all of our n's going all the way up. Reason for that being, the individual degree of each x in both A series and B series must all line up exactly the same if the sequences, or if the sum of the series, the values of the series are actually equal to each other. Because again, this needs to work for every possible x value that we could ever think of. All right, we define the degree of A of x to be the smallest n such that A of n is not 0. Smallest n. That's fun. I don't like that. I mean, it's not... Obviously, I have nothing to do with it. But I want to say, like... From intuition, I want to say that the degree of an infinite series would end up being like the value n for which every coefficient greater than n, a sub for all a sub n plus k, they're all 0. That's just how I would want it to be said, but obviously, again, I have nothing to do with it. It's not my business. Smallest, okay. So practically every pretty much every power series that I know off the top of my head is just going to be degree 0, according to this. Okay, so we also write x to the n times a of x can be defined as a sub n. It's not times. I don't know what the notation is exactly, but point being, right, we're really looking for what's the coefficient of that particular x to the n term. It is a sub n. So therefore, a of 0 can be defined as finding the coefficient of the x to the 0 term, which is a sub 0. We also define formal power series inspired by series from analysis, such as e to the x is defined infinite sum of x to the n over n factorial. Negative log of 1 minus x is defined as the infinite sum of x to the n over n. 1 plus x, all raised to the r, is defined as the infinite sum of r choose n times x to the n for any complex number r, where r choose n is r times r minus 1 times etc. through r minus n plus 1, which is r minus parentheses n minus 1 over n factorial. The ring C bracket x is commutative with 0 equals 0 plus 0x plus 0x squared, etc., and 1 equals 1 plus 0x plus 0x squared, etc. It is an easy integral domain. That is, a of x times b of x equals 0 implies that a of x is 0 or b of x is 0. So again, standard zero product property. Infinite sum of a sub n x to the n is invertible if and only if a of 0 is not 0 itself. Okay. For example, 1 over 1 minus x is equal to 1 plus x squared plus etc. Because if we multiply the other side by 1 minus x, right, 1 minus x times the infinite sum that we have, we get 1 equals 0x plus 0x squared, etc. Okay, so invertible. I believe we're about to be yanked into ad breaks, so sorry about that. But we'll be back in 3 minutes. Thank you, everybody, for coming. And we'll finish up at least a couple more pages. So see you in just a little bit. It's been a while since I've shown this guy off on stream. I had entirely primed one of my, or well, all of the four horsemen of the apocalypse, who are in our TTRPG, which, by the way, we're doing. Who's it? We're doing TTRPG prep on Thursday nights. So if anybody's interested in that, come on over. I'd shown off the four horsemen of the apocalypse, who are Orions, who are a series of robot people who have been sort of infected by a bunch of nanobots who are controlling them via what one would call magical means, I suppose. And so I entirely primed all of them. This is Death, as is now like 80% done, probably. So we're getting there. We want to get the stones in as well here. The idea is that Death is effectively going to be from a volcanic area, so it's going to be like ash and mostly obsidian type rock. I gave this one a coloration of what's called dryad bark, so it's more of a very deep brown color instead of black, but it's looking pretty good, if I do say so myself. Best job I've ever done, certainly. I need to dry brush all of these like little intricacies on here in a gold color, and I don't have a gold color. I have what's called Balthazar gold, but it looks copper. So I was like, all right, let's go get an actual like gold color and dry brush this guy next time. So I'm going to be heading over to the shop, the gaming shop tomorrow, and get some paints. All right. So, convergence. When working in C bracket X, we will not consider convergence of sequences or series of complex numbers. In particular, we will never substitute a complex number x into a formal power series A of x. However, we do need a notion of convergence for sequences in C bracket X. We say that a sequence a sub 0x, a sub 1 of x, a sub 2 of x of a formal power series converges to a of x equals said sum if the limit as n goes to infinity of the degree of a sub n of x minus a sub x is equal to infinity. That is, for any little n in natural numbers, the coefficient of x to the n in a sub m of x equals a sub m, nope, a sub n for all sufficiently large m. This gives us a useful criterion for convergence of infinite sums and products in C bracket X. The sum of all a sub j of x converges if and only if the limit as j goes to infinity of degree of a sub j of x is infinity. Okay. So the right side is saying that we need an actual infinite series. So we can't just get 0 times x to the whatever. It's got to be a non-zero coefficient. And so those non-zero coefficients are going to stretch off into infinity. And we need to look at all effectively subsequences of the big sequence A of x. So as long as it is literally infinitely long, we have as many individual terms as we want, then we're good. On the other hand, the product of 1 plus all of those individual sequences will converge. If and only if the same thing. We have an actual infinite series where a sub j of 0 is equal to 0. For example, the infinite sum series as x plus 1 to the n over 2 to the n does not converge in this topology. Because they're all of the same degree, right? Every individual term is of the same degree. Maybe not. Hang on. Note the coefficient of x to the 0 in the sum cannot be obtained through finite computation. Oh, okay. Yeah. It would require interpreting the infinite sum 1 over 2 to the n. On the other hand, the following infinite sum converges. Infinite sum of 1 over n factorial times negative infinite sum of m going from 1 of x to the m over m, all raised to the n, is equal to 1 minus x. It's clear from the criterion above that this series converges, but why does it equal 1 minus x? Because it is the same as something we saw up here. I suspect this one. Or, yeah, right, because this is going to end up making this an alternating series. And we're doing effectively 1 minus x raised to the first power. So that's going to be every term is going to be 1 choose n. Of negative x parentheses to the n. One choose? That feels awkward. Borrowing from analysis. In C bracket x, 1.6 is an algebraic identity which says that the coefficients of x to the k in the left-hand side, for which we can give an ugly but finite formula equal to -1, 1, 0, 0, 0, 0, 0. If we were to follow a purist algebraic attitude, we would give an algebraic or combinatorial proof of this identity. This is probably possible, but intricate and rather dogmatic. A much simpler approach is to shift toward an analytical attitude, at least momentarily, and recognize that 1.6 is the Taylor series expansion of e to the negative log of 1 minus x, where log is natural log, which is just 1 minus x, for absolute value of x less than 1. Then we could just invoke the following simple fact from analysis. If two analytic functions are equal in an open neighborhood of 0, then their Taylor series is 0. No, their Taylor series at 0, also known as the Maclaurin series, are equal coefficient by coefficient. That is, they're equal as formal power series. Composition. The composition of two power series a of x and b of x with b sub 0 equals 0 is naturally defined to be the following. Note that this sum converges if and only if b sub 0 equals 0. Two very important special cases in combinatorics are the series 1 over 1 minus b of x and e to the b of x. Calculus. We define the derivative of a of x to be the infinite sum of a sub n times x to the n to b. A prime of x is equal to infinite sum of n plus 1 times a sub n plus 1 times x to the n. This is weird, but it's absolutely true. So what we're seeing here is that normally we would take down the n as a exponent, bring it down front, and then be left with n minus 1 in the exponent of x. However, this also eliminates n equals 0, because if n is 0, then 0 comes down and it multiplies and it clears out everything. So we can't have that. So what we do is we renumber everything and say, okay, so we can't do n equals 0. We're just going to have n be greater than or equal to 1. Or we renumber everything so that n now becomes n plus 1. And then our n minus 1, which was in the exponent, is now just n. Normally I would do it with a different letter so that it doesn't bother people, but in this particular case, right, people should have taken calculus and understand how coefficients or how calculus works, how derivatives work. And then also you should know how to reassign variables inside of a series. Should. Formal derivative satisfies the usual laws of derivatives, such as a plus b derivative equals a derivative plus b derivative. AB derivative is equal to a derivative b plus a b derivative. And a of b of x derivative is equal to a derivative of b of x times b derivative of x. We could still solve differential equations formally. Nice. For example, if we know that f prime of x equals f of x and f of 0 equals 1, then natural log of f of x all prime is equal to f prime of x over f of x, which is 1. which gives natural log of f of x equals x, and therefore f of x is equal to e to the x. This concludes the discussion on formal properties of power series. Now let us return to combinatorics. Ordinary generating functions. Suppose we are interested in enumerating the family fancy A is equal to a sub 0 union a sub 1 union a sub 2 union etc. of combinatorial structures where a sub n is a finite set consisting of the objects of size n. Denote by absolute value of a being the size of a within fancy A. The ordinary generating function of fancy A is a of x is equal to the infinite sum where a belongs to the fancy A set of x to the absolute value of a is equal to a sub 0 plus a sub 1x plus a sub 2x squared plus etc., where a sub n is the number of elements of size n. We are not interested in the philosophical question of determining what it means for fancy A to be combinatorial. We are willing to call fancy a combinatorial structure as long as a sub n is finite for all n. We consider two structures, fancy A, fancy B, combinatorial equivalent, and write fancy A is equivalent to fancy B if a of x is equal to b of x. I like it. I don't like, however, the fact that the music just cut off and didn't... Oh, no, it's still going, apparently. Just a very quiet song, I guess. More generally, we may consider a family fancy A where each element A is given by the weight, Wt being weight of A, often a constant multiple of x to the absolute value of a, or a monomial in one or more variables x1 through xn. Again, we require that there are finitely many objects of any given weight. Excuse me. Then we define the weighted ordinary generating function of fancy A to be the formal power series a sub weight of x1, x2, x3, etc. to x sub n is equal to the sum of all weights of A. Examples of combinatorial structures with their respective size functions are words on the alphabet set 0, 1, length, domino tilings of rectangles of height 2, width, or dike paths length. We may weight these objects by t to the k, where k is, respectively, the number of ones, the number of vertical tiles, or the number of returns to the x-axis. Operations on combinatorial structures and their generating functions. There are a few simple but very powerful operations on combinatorial structures, all of which have nice counterparts at the level of ordinary generating functions. Many combinatorial objects of interest may be built up from basic structures using these operations. 132. Let fancy A, fancy B be combinatorial structures. Fancy C is equal to fancy A plus fancy B disjoint union. If a C structure of size n is obtained by choosing an A structure of size n or a B structure of size n, then C of x is equal to A of x plus B of x. This result also holds for weighted structures where the weight of a C structure is the same as the weight of a respective A or B structure. C equals A cross B, product. If a C structure of size n is obtained by choosing an A structure of size k and B structure of size n minus k for some k, then C of x is equal to A of x times B of x. This result also holds for weighted structures of if the weight of a C structure is the product of the weights of respective A and B structures. C is sequence of fancy B. Assume absolute value of fancy B of 0 equals 0 if a C structure of size n is obtained by choosing a sequence of B structures in total size n, then C of x is equal to 1 over 1 minus B of x. This result also holds for weighted structures if the weight of a C structure is the product of the weights of respective B structures. Okay. Fancy C equals fancy A composed fancy B. Compositional formula, assume that absolute value B sub 0 is 0 if a C structure of size n is obtained by choosing a sequence of, say, k, B structures of total size n and placing an A structure of size k on this sequence of B structures. Then C of x is equal to A of B of x. This result also holds for weighted structures if the weight of C structure is the product of the weights of A on its blocks and the weights of B structures on the individual blocks. Lagrange inversion formula. Fancy C equals fancy A inverted. Algebraic version. If A, -1, of x is the compositional inverse of A of x, then n times x to the n, A -1 of x is equal to bracket x to the n minus 1 times x over A of x all raised to the n. Combinatorial version. Assume fancy A of 0 has an absolute value of 0. Fancy A sub 1 has an absolute value of 1. And let A of x equal x minus A sub 2 x squared minus A sub 3 x cubed minus A sub 4 x to the fourth, where A sub n is the number of A structures of size n for n greater than or equal to 2. Let an A decorated plane rooted tree, or simply A tree, be a rooted tree T where every internal vertex V has an ordered set D sub V of at least 2 children, and let each set D sub V be given out an A structure. The size of T is the number of leaves. Let C be the generating function for A decorated plane rooted trees. Then C of x is equal to A inverted of x. This result also holds for weighted structures of the weight of a tree is the product of the weights of the A structures in its vertices. Okay, well, we're not going to get anywhere on that one. So let's go ahead and move out from here. I know we said Dr. Gold is currently giving away gold or something like that. So we'll head on over and see what Dr. Gold is up to. I hope you all are having a lovely evening, and we'll be back on we'll be back tomorrow playing some blueprints, and then we'll be back on Wednesday hopefully doing some math calculation stuff for GRE type things. And I'm looking to get some stuff done for our YouTube, so if anyone is interested, head on over to our YouTube channels at Obi-Wan-Pez and at nsimplexpachinko6542. If you just search Obi-Wan-Pez or nsimplexpachinko, you should find me. So good luck out there, stay safe, and we'll see you next time. Thanks for coming, everybody, and yeah. Hope you all have a great 10 seconds. All right, got to fill this time. I don't know what to fill the time with, honestly. So I hope you all are having a good week, and hope you all continue to have a good week. I'll see you later. Thanks, everybody. My name's Obi-Wan Pez. This is NSimplex